right?
Yes.
So we're very excited today to have another speaker from the University of Chicago, and it has nothing to do with geographic proximity, as you may think. It has more to do with the title of his presentation and what he does. So we're pleased to have Professor Risi Kondor from the Computer Science Department of the University of Chicago. He studied both theoretical physics and mathematics at the University of Cambridge, did his master's at the machine learning program or department now at CMU, PhD at Columbia, postdoc at the Gatsby Institute at University College London, and Caltech, right?
Exactly.
And now he's our neighbor at the University of Chicago, and he's one of the very few people in computer science that understands the challenges on integrating deep learning, machine learning with physics. So he will be talking today on covariant neural networks for learning from graphs, molecules, and almost anything else. So that way, whatever, if you don't fit in, you must be fit in on anything else.
Okay. All right. Thanks very much for that introduction, Nicholas. All right. So yeah, this talk is going to be about certain things and certain other things and everything else. So you can kind of listen to it at different levels. You can either take it as a prescription of certain neural network architecture for solving specific problems, or you can get the more general message about the structure of deep learning networks in general, and to me, this fascinating problem of combining the really two different cultures: the culture of physical simulation with the culture of stochastic or statistical simulation that really machine learning and AI is about. Okay, so the two specific kinds of problems that I'm going to talk about, actually they both relate to problems in physics or chemistry. One of them is learning from graphs, and it's not a coincidence that I have a small molecule over there, because that's exactly the canonical domain in which this occurs, and maybe one of the most interesting domains from the science point of view. So you can think of drug molecules, for example, which really are just captured by these small graphs, and you want to learn some property of them, like some biological activity or some physical property, like, I don't know, the boiling point or the total energy of the molecule or something like that. And the other thing is learning force fields. So that's in the context of, so more generally, of course, you want the learning properties of physical systems defined by the positions of the atoms is a general fascinating area, but a very specific problem is, okay, now I give you this system consisting of a number of atoms. It's a crystal or a large biological molecule or something, and I want to simulate it, so I want to do molecular dynamics. Then do I really need to run quantum mechanics, something like density functional theory, at every single time step to be able to integrate the system forward in time, or can I actually learn the interactions of between the atoms, so the forces on the individual atoms as defined by the positions of their neighbors? Okay, so I'm going to taking a neural networks approach to this, and at some level, the kind of learning algorithms we're going to talk about really are very similar to this standard picture of neural networks that is taught in all the machine learning classes. So you have neurons, usually arranged in a certain number of layers, and they propagate information from one layer to the next layer, and each neuron at the end of the day does something fairly simple, usually taking a linear combination of its inputs followed by a nonlinearity. Even the nonlinearity has steadily been becoming simpler and simpler, so now it's a lot of the time is just one of these ReLU functions. And if you combine enough of these neurons and have a sufficient number of layers, then of course you can learn fairly bizarre functions. What's surprising is that by having the right update strategy for the weights of the neural networks, for the right back propagation rule, you can actually learn remarkably efficiently, especially for the kind of problems that people are interested in. Okay, so the very standard architecture in the applied side of neural network research, in particular in all the vision problems. So think image recognition, which is really the domain where neural networks have kind of consistently had remarkable success, are these convolutional neural networks. So there, the picture, there's a lot of regularity in convolutional neural networks. If you take a slightly more mathematical point of view, then what happens as a convolutional neural network is that each layer just implements the composition of two operations. One of them is a convolution of the input to the layer with a filter, and the next one is a pointwise nonlinearity. And then in the next layer, you again do convolution followed by the pointwise nonlinearity and so on. So you can think of convolutional neural networks in this very concrete manner in terms of these grids and representing the functions, the activations as tensors, and then you move this filter across the tensor and then you multiply them together, blah, blah, blah. But slightly more abstractly, this is what's really happening. It's this the sequence of these alternating convolution operations and pointwise nonlinearities. And by convolution, I really mean the classical notion of convolution given by this formula, right? So you just convolve the filter as a function with the activation of the previous layer. You convolve it with the filter as given by this formula. Okay. So the complication is, or the reason that this is it's not quite as simple as what you might think based on the first line, is that then you have many layers. So the number of layers has been steadily increasing over the years, and then you have many channels, and you need to be very careful about how you set up the size of these filters. So there is some amount of black magic in the community. This, I believe it is AlexNet, is one of the famous neural networks which proved to be shockingly effective at image recognition. So there's a lot of detail in exactly how it looks on the inside, and at the end you might have some other neural network tacked on which is not quite convolutional. But fundamentally, at least from the mathematical point of view, what happens is fairly clear, and when you look inside, it's also very instructive to see what the network learns. So in particular, how the convolutional structure is reflected in what the network learns. So what this shows is the top patches. So you look at individual neurons in the network, and then you go back at the data and ask yourself which patch of the input is this particular neuron most sensitive to. So what you see here is that the second layer of this convolutional neural network, the individual neurons really pick up very simple features, as kind of you would expect, because they are local, right? They're just based on a small neighborhood of the given neuron. So they are essentially like line detectors, or maybe they pick up these splodges of different colors. This is already a little bit curvy, but still these are very simple visual features, the kind that you would also expect in like animals' visual system. Okay. So this is then the third layer. Okay, how many? Yeah, where you still have relatively simple features, but they seem a bit like they are like compositions of these features from the earlier layer. So they are a little bit more complex, and they can capture more informative visual features from the images. And then you look at the fourth layer, and all of a sudden you see that you've got a neuron which it picks up, I'm not sure if you can see it from that distance, but this is like a dog face detector, okay? So in 4 layers, you went from detecting edges and little curvy bits and little splodges to detecting the semantically meaningful features. Okay? So that's an even better dog detector over there, okay? So somehow, these relatively simple architectures are surprisingly effective at picking up the interesting features from images. And indeed, the history is that something that when these could really be implemented at scale, and in particular when the community went from looking at relatively shallow networks to deeper and deeper networks, performance just kind of skyrocketed, right? So these just completely wiped out all the previous approaches in image recognition, because like every year there was like a doubling of performance in terms of these benchmark data sets. Okay, so all this is very good, and it's not very hard to see the economic impact and the success and the hype around all these algorithms if you just open the New York Times or any news source today. But to be truthful, most of what we do in machine learning is still today, especially in deep learning, is still centered around this sort of task. So we've got this down. What I'm interested in is kind of generalizing this to scientifically more relevant and maybe more interesting problems. And in particular, what I'm going to talk about today is how to generalize this notion of convolution and why convolution is important in the first place. Okay? So actually, in the image recognition context, it's relatively easy to understand what the role of this convolutional nature of the network really is. So what convolution does for you is that it guarantees equivariance. And equivariance literally means that if you take the image, the input to the network, and you translate it, then the activations in the second layer are going to translate the same way. The activation in the third layer is going to the same way, and so on up to the top of the network. At the very top of the network, you might do something which just symmetrizes overall translations, because ultimately what you want is a neural network that is not sensitive to where this object that you're trying to recognize is in the visual field. But the way you implement it is that each layer is not invariant, it's equivariant, right? So they have this predictable transformation of the information at each layer of the neural network. So convolution guarantees this property, and in fact you can prove relatively easily that if you want this property, then essentially you are forced to have a neural network which has this convolutional structure. A variant of convolution is steerability. So there things get a little bit more interesting when you also consider rotations. So for simplicity, just rotations by multiples of 90 degrees. You want a similar sort of property there if you want to have rotation invariant image recognition. But you can't just use equivariance in the same sense, because your filters are directional, right? So you're going to have vertical edge detectors and horizontal edge detectors. So when you take your image and you rotate it by 90 degrees, then sure, the activations are going to move around. But in addition, the vertical edge detectors are going to be exchanged with the horizontal edge detectors, right? So in addition to this, translation action on the activations, something also happens to the internally to the activations of a specific neuron in the network corresponding to a particular pixel in the higher layers. But that can still be handled with this relatively classical device of steerability. This has a long history in signal processing, steerable filter banks, and so on and so on. So there is a prescription for how to build neural networks which also behave appropriately with respect to. Okay, so this is just an illustration of this from a paper by Cohen and Welling, how to behave appropriately with respect to rotations. So a lot of the work that we're going to talk about was actually inspired by a student of mine who got into deep learning before me. He was a student at TTI, Toyota Institute in Chicago, which is like the co-located on the University of Chicago campus. He just graduated and went on to Brown to do a postdoc. But fundamentally, the question he asked, and we started thinking about maybe 2 years ago, is then, what is the generalization of this notion of convolution to other types of data then, or other types of domains, in particular to graphs? Okay. So actually, the two applications that I mentioned at the beginning involve answering this question. And the solution that I give is going to have a similar flavor, but still going to be different in the two cases. In both cases, it's going to involve a combination of two components. One of them is this idea of compositionality, that you have a complex object, and you break it down into parts. And then those parts you break down into subparts, and the subparts to sub-subparts, and so on and so on. So this is very natural to do on a graph, for example, because you have subgraphs. It's also very natural to do with the atomic environment, right? So you have just physical subsystems. And the idea is that the structure of a neural network is going to have to reflect this compositional structure. Okay? So this hierarchy of parts and subparts, the parts are actually going to correspond to the neurons. And the claim is that this is kind of already implicit in ordinary convolutional neural networks, because if you ask yourself what part of the original image is this particular neuron responsible for? Well, it's everything that's underneath it, right? It's all the input pixels that can propagate information to that neuron. And that exactly defines this parts and subparts and sub-subparts kind of structure. So it's the same sort of thing, except that in the case of images, of course, this whole composition graph is much more regular because it just comes from the 2D grid. But this is what's required to for the neural network to be able to capture information at multiple different scales, right? So that's critical in image recognition, to be able to capture the little local things and the slightly bigger things, and you're able to capture the interaction between the little local things and so on. You want information from all of these different scales. And the claim is that it's also going to be critical for capturing the structure of molecules or for capturing the properties of these atomic systems. The other component, which is maybe even more interesting, is the covariance component. So that is what in the case of ordinary convolutional neural networks is just equivariance. That there is a natural notion of symmetry here. There's a group acting on the data in the first place. In the case of convolutional neural networks, that group is just the translation group. And you want everything in the neural network to behave properly with respect to that action. The simple thing is if everything is invariant. So in the case of graph neural networks, for example, you could say that, okay, I want all the activations to be invariant to how I number the vertices, because that's totally arbitrary, right? I can renumber the vertices, and I don't want the output of the neural network to change. But our claim here is that actually invariance is not necessarily the right thing to do, because if you enforce invariance internally in the network everywhere, then you lose a lot of information. And that's easy to see, again, in the classical case, because what would invariance to, say, rotations mean? It would mean that there's no difference between horizontal and vertical filters. I solve this rotation problem by just having one type of filter. And it's clear that you're going to lose a ton of information if you are not allowed to distinguish between horizontal and vertical filters at the lowest level. So covariance is the generalization of this idea, and it's much like steerability. It says that I am allowed, so the activations are allowed to change, but they change in a prescribed way, in a prescribed and controlled way. Okay, so this is kind of the plan for the talk in some sense. So in the first part, I'm going to talk about some theory which is inspired by tools from algebra, non-quantitative harmonic analysis in particular, which gives a prescription for how to build such networks. And in the second part, I give the specific examples. Okay. So again, this is what happens in classical convolutional neural networks. The activations translate the same way as the inputs do, and this guarantees equivariance. So the question is, what is the generalization of the notion of equivariance when the group is not just the translation group, it's something else? And what is the corresponding notion of convolution that is going to guarantee that the neural network satisfies this property? So it's good to have a mental picture of what the group is and what the domain is and how they interact. So the simplest possible setup to imagine is actually stuff on the sphere. Okay? So in that case, so this would be like object recognition on the sphere, which is exactly something that we recently had submitted a paper on. So the setup here is that it's, again, image recognition, except that now the image is not on the plane, but it's painted onto the surface of a sphere. And the group is not the group of translations, but it's the group of three-dimensional rotations of space, i.e. it's the rotations of the sphere or the image on the sphere together with the sphere itself. And this already highlights one departure from classical convolutional neural networks, in that the space that the data lives on is no longer the same as the group, right? So the image is now on the sphere, but the group acting on the image is not the sphere, it's the rotation group. So the two are related, but they're not the same anymore, okay? So this is formalized the following way, that our function lives in a space X, X being the sphere here. We have a group, usually it's a compi group, acting on X, And what it does is that it drags whatever function we have on defined on x. It drags kind of the function with it. So formally, this is how the function changes. This is the induced action of the group on functions. And what we want is we want a neural network that is equivariant with respect to this action. So this distinction between the space on which the data lives and the group makes things a little bit more complicated because the space can actually change from layer to layer. So whereas in a classical convolutional neural network, everything was on the plane, in principle, in one of these generalized equivariant neural networks, each layer can be a different space, but each space is acted on by the same group. So these spaces are usually called homogeneous spaces of the group. Okay. So anyway, this is just a slight complication to have in mind. So this means that when you look at two different layers, so you have space x1 and x2, then you're going to have two different actions of the group, and that's going to induce two different actions of the group on functions. And then the notion of equivariance is that these two different actions are going to commute with what the neural network is computing. So if you take the original input and you squeeze it through the neural network, then you get phi of f. Okay, and if the group first acts on it, so if you first rotate the sphere and then you push it through the neural network, then you would get the same thing as if you first pushed it through the neural network and then the group was out to act on the activations. Okay, so the mathematicians would depict this in terms of a commutative diagram like this. So the idea is that you have start with a function on the space x1, and no matter whether you first apply the rotation and then go to the space x2 or the other way around, you end up with the same thing. So it's a commutative diagram because it doesn't matter which road you take. Okay, so this is the notion of equivariance that we want from one of these generalized convolutional neural networks. Now, what is the generalization of convolution then? So actually, there is a natural generalization of convolution to groups, at least to compact groups, and it's kind of exactly what you would expect. So in ordinary convolution, up there, sorry, I'm not sure if I can, oh good, okay. So up there, you would have u minus v gv, right? So on a group, you can't subtract group elements, instead you take the inverse of a group element. But otherwise, this is just a straightforward generalization, the natural generalization of convolution from functions on the plane to functions on a group, such as the rotation group. Okay, so this is well established as standard convolution on the group. Now, you might say that this is fine, but again, we don't have functions on a group. We have functions on these x spaces which the group acts on. So it turns out that's not a problem, because there's a natural way that those functions kind of induce functions on the group itself, and you can go in the other direction and correspondingly define a function, even if there are functions on the group, functions on those homogeneous spaces rather than functions on the group itself. Okay, so what is this thing? Again, going back to the example of functions rotated on a sphere, this really is just convolution, or if you wish, correlation on the sphere. So you have the image on the sphere, and you have this little filter, which is again a little function on the sphere, and then the correlation between the image and the filter literally is going to tell you, if I take this filter and move it around on the sphere into all these different positions, then how much is it going to overlap with my image? Okay, so this is exactly what you would expect. This is just the mathematical formulation of that thing. So what's even nicer is that there is also a generalization of the notion of Fourier transformation to groups. Okay? So in the classical case, Fourier transform is, as we know, is given by this formula. And that's relevant to convolutions because the convolution theorem tells us that if you take two functions and look at their convolution, then the Fourier transform is just going to the product of the corresponding Fourier coefficients. So convolution is something that looks really nice in Fourier space. In fact, this formula is used all the time just to make convolution numerically more tractable. Okay? Now it turns out that there's also a generalization of Fourier transformation to groups, at least compact groups. And it's given by this formula. So you just compare that with that. And you see that it has follows the same, morally the same thing, right? So you take your function and you integrate it over your group, weighted by something. It's the same thing here, except what you're weighting here, these are called the irreducible representations of the group. So these are actually matrix-valued functions, which somehow capture what the group actually does when the group acts linearly on some space, what it actually does. So if you've never heard of representations before, then you just need to take my word for it that this is something that's well tabulated for most commonly occurring groups. It might be a little bit too painful to write down the elements of these matrices explicitly, but it's something that is well within the realm of present-day mathematics, and it comes up all over the place in physics and in certain engineering applications, and of course it has this really rich mathematical theory. Okay. So what's important for our purposes is that, lo and behold, the group convolution also looks nice in the group Fourier transform space. Okay. So you take two functions and you apply this group convolution that I had in the 2 slides back, and you look at its Fourier coefficients. The Fourier coefficients are now matrices because this thing is a matrix, so the individual Fourier coefficients are matrices. And it turns out that those Fourier coefficients are just the matrix products of the Fourier matrices of the function and the Fourier matrices of the filter. Okay. So this is a crucial equation, maybe the only equation that I really want you to remember from the talk up to this point. Okay. So why is all this? Why after starting to talk about molecular and so on, why am I suddenly talking about abstract algebra? So this is a theorem that we proved in a paper that came out at ICML this year. And it basically gives a prescription for how to build group equivariant neural networks. It says that if you have a feed-forward neural network, which was equivariant to the action of a transformation group, as I defined earlier, then necessarily each layer of the neural network implements one of these generalized convolution operators. So there's no choice. This is the only way to do it. If you want to build a neural network which is going to transform appropriately according to rotations of 3-space, because you want to learn something related to 3-space like the forces in an atom, then each layer must actually do this group convolution. Okay? And now you think of it in terms of this. So I don't want to go too deep into what the interpretation of this theorem or the way to prove it. But if you think of it in terms of the convolution formula here, okay, so that means that what each layer of the neural network does is that it just multiplies together these Fourier matrices, right? So these are the Fourier matrices from the previous layer. So what the layer does is that it multiplies them from the right by another matrix. So what that means is that first, the information from the different, captured by the different matrices are not allowed to mix, right? So for the rotation group, for example, here you would have a 1-dimensional matrix and a 3-dimensional matrix and a 5-dimensional matrix and a 7-dimensional matrix and so on and so on. But because the layers operation can only be of this form, these different matrices, they cannot be mixed through the action of the neurons. They are independent. The other thing is that even within the same, for a given matrix, because what happens is that it just gets multiplied by something else from the right, you're only allowed to mix columns with each other. So that's the only thing that convolution really does. It takes these matrices and mixes their columns with each other. But they're not allowed to mix the rows. So that's a very sort of stringent constraint on what the neurons will actually do. Okay? So in terms of this more kind of functional analytic point of view, it says that first you have the space of space of all possible activations, and it breaks down into subspaces corresponding to the individual matrices, and those subspaces are conserved by the convolution, but even those subspaces break down into smaller subspaces corresponding to individual columns of the matrices, and those subspaces are individually conserved. So this is what we had to prove. And proving it in the forward direction, that if something is a convolution operation, then it's going to give rise to an equivariant neural network, that was easy. Going in the opposite direction actually gets a little bit technical. So this is the only way you're allowed to construct these neural networks. So why is this interesting? Okay. So again, it's interesting because it says that a neural network is going to have to deal with these funny functions on spheres or in other more general spaces that the group is acting on. But actually, if you represent those functions in Fourier space, then the neural network is only going to be multiplying matrices together. And that's exactly what neural networks are good at, right? So if you use PyTorch or TensorFlow, it's all about tensor operations. So we started with something which seemed like a slightly foreboding problem, like doing these convolutions on the sphere, like integrating over the rotation group and so on. But actually, it's not so on Fourier space, it's not foreboding at all, because it's just the usual thing. The neural network is going to be multiplying matrices together. Okay. So there's actually a little bit more to it, because in the paper we looked at what the structure of these matrices. So what the fact that the function is not on the rotation group itself, but say on a sphere, actually means that these Fourier matrices are going to have very specific structure. They're usually going to have this column sparse, just kind of stripy structure. And then the filters, I mean, there's no point in that means that the filters are going to be row sparse, because there's no point in putting anything else over there, because it's going to be multiplied by zeros anyway. Okay. And then the output, when the output also needs to be column sparse, but according to the structure of the next layer. So that means that the filters are actually going to be row sparse and column sparse. Okay. So now I'm telling you that not only is it the case that the operation of the neural network in each layer must be reducible to this sort of matrix multiplication, but it's also matrix multiplication with matrices over the specific structure. So it's really a prescription for how to build these neural networks. So it's a very strong argument I think it's a very strong argument in terms of building these generalized convolutional neural networks to work in Fourier space. Okay? And actually, it meshes well with this idea of compositionality that I talked about earlier, that each of the neurons actually correspond to some part of the input object. But now we also know that the activation of these neurons is not just going to be a scalar, but it's actually going to be one of these Fourier transforms. So it's one of these bunches of matrices. And each one of them is literally just going to do this convolution operator followed by an appropriate nonlinearity. So here in this talk, this is made very explicit, but actually a number of papers have come out recently which implicitly do the same thing. So Tucker Cohen and his collaborators had a paper on spherical convolutional neural networks, and they also attacked this problem from the point of view of these generalized Fourier transforms. There's been a sequence of papers recently on generalizing convolutional neural networks to manifolds. If you look carefully, then actually it's a very similar idea. The manifolds have a slightly looser structure than groups or homogeneous spaces of groups, but fundamentally it's pressing against the same harmonic analysis ideas. And there's also this literature on neural networks for graphs, which I'm going to talk about next, which under the hood also deals with the same invariance problem. Okay. So after this general part of the talk, I want to go into the specific application of doing neural networks on graphs then, because I will see that actually all this algebra, machinery, and so on, when you look at it in specific cases like for graphs or the rotation group, it's not that frightening after all. So this business of learning from graphs is not new in machine learning. Even like more than 10 years ago, I had a couple of papers on learning algorithms for graphs. Even at the time, this was motivated by these problems for learning from molecules. But of course, That was 10 years ago, so instead of using a deep learning approach, we used the kernels approach. So we tried to map all these graphs into Hilbert space somehow. Okay. But so there's this whole there's this whole sequence, this whole stream of machine learning just around this problem. How do we learn from graphs? It just comes up so many different times, and but at the end of the day, the problem always boils down to, sorry, what happened here? It always boils down to this this headache of trying to satisfy two things simultaneously. Okay, three things simultaneously. Okay, so when you're talking about learning from graphs, there is a natural group that you want to be invariant to. And that group is the symmetric group, the group of permutations acting on the vertices of the graph. So that's just saying that if you give me a graph and you label the vertices, 1, 2, 3, 4, 5, 6, 7, well, you give them the same graph with the vertices labeled a different way, then that shouldn't make any difference to how the graph is classified. Okay. The other important thing is that graphs, at least interesting graphs, intrinsically have this multi-scale structure. So when you want to say something about a molecule, what you're interested in are, of course, what atoms are there in the molecule. And also, what functional groups there are. So that's small groups of atoms connected in a specific way. And then how do the functional groups relate to each other? And then how do larger parts of the molecule relate to each other? So just like in the image recognition case, this multi-scale structure is really essential for learning from graphs. So here comes the compositional approach. Let's try and capture the multi-scale nature of graphs by building this hierarchy of subgraphs. So we start with the smallest subgraph. And this is like the one neighborhood of every vertex. And then we look at larger subgraphs. There's a 2 neighborhood of every vertex, and 3 neighborhood, and so on and so on. And let's build a neural network where the neurons actually correspond to these subgraphs. And the way they're connected is just by inclusion. Like what one neighborhood does this 2 neighborhood include as a subgraph, and so on and so on and so on. Okay. So this approach is so natural. Another way to, so if you build such a neural network and you run information from the lowest level subgraphs, which are essentially just individual vertices, to the top level, which represents the entire graph, then essentially what you're doing is you're just propagating information from vertices to other vertices. So another way to look at the same thing is in terms of this message passing scheme, that you initialize the graph by giving a label to every vertex, something like a label corresponding to what sort of atom is sitting there or how many neighbors it has or something. And then you have k rounds of a process where in each round, each vertex collects the information from the neighbors and then does something to the information, hopefully something nonlinear. So it kind of processes the information, but in such a way that it treats every neighbor the same way. So what the representation you get is going to be invariant to local permutations. And then that updates its own label corresponding to what the result of this aggregation operation is. And then you iterate. So then you have several more rounds of this operation. So this is really just the same thing. And in fact, this message passing idea was picked up by the neural networks community. And there's a whole sequence of papers on different variants of this to build neural networks that recognize graphs. Okay? So in particular, it was this paper by Gilmer and al. which formalized the fact that these are really variations on the same idea and gave this general name of message passing neural networks to this stream of work. So the nice thing about these message passing neural networks is that by construction, they afford this hierarchical representation of the graph. And in addition, it's guaranteed to be invariant to permutations, because every single step of the message passing process is invariant to permutations. Literally, it says that you collect all the messages, all the information from the neighbors, then average them, which is an invariant operation, then apply a nonlinearity, and that's going to be your own label. Okay. Now, the not so nice thing about this message passing neural networks is the same thing, is that at every layer, at every neuron, the activation is invariant to the permutation of the local neighborhood. So this, if you draw the analogy with the convolutional neural networks literature, then this is some kind of convolutional neural network. You have these local filters, and there's a hierarchy of them, and globally you satisfy invariance. So that's all very nice. But this thing is locally invariant as well. So in the convolutional neural networks analogy, that would mean that at every layer, you're symmetrizing with respect to rotations. So there is no difference between horizontal and vertical filters. Okay. So the question we ask in this regard is, can we do better? So the type of problem that this gives rise to is that essentially what it means is that the identity of vertices is lost immediately. So you compare these two different situations. So here, these two vertices send a message to that vertex, and these two vertices send a message to that vertex, and then in the second round, the messages from these two vertices are collected over there. Okay? Now compare these two different graphs. So they are two different graphs, but in terms of what vertex 3 sees, they are the same, right? And vertex 2 sees, they are the same. And then since vertex 1 only accesses information from 4, 5, and 6 through 3 and 2, vertex 1 is not going to be able to tell whether this is the situation or that is the situation. So it just can't tell that these two vertices are really the same vertex in the top graph, whereas in the bottom graph, they're not the same. Okay. So our solution to this problem is to build covariance into the neural network. So we are going to have this compositional structure. This is reflected in the structure of the neural network. Every neuron corresponds to one of these subgraphs. And the output or the activation of every neuron is going to be now quantity, in particular a tensor quantity, which is not invariant with respect to local permutations, but is covariant with respect to local permutations. So in particular, the way we define this is that we're going to have zeros, first, second, third, and so on order tensor activations. So a 0th order tensor activation is basically just a scalar. So a single number, and the way that behaves with respect to local permutations is that it does not change at all. A first order activation is a vector, and the way that behaves under permutations is that the components of the vector are permuted by the permutation. So it's like the permutation matrix acting on this vector on the left. And the second order activation is a matrix, and the way that behaves is that permutations permute both the rows and the columns. So it gets multiplied by the permutation matrix from both the left and the right. And in general, sorry for the skipping. So in general, for a kth order tensor activations, it's a kth order tensor, where each dimension is permuted by the permutation matrix. Okay. So then the question is, this is a prescription. This is what we want from the activations, very similar to what we want from a covariant neural network in terms of this equivariance property. But how do we actually build a neural network which can do this, which is guaranteed to give activations which transform in this way? And it turns out that you don't need to look very far to find the right operations, because you just write down your standard tensor operations, and it turns out that they automatically satisfy this property. So if you take one of these two different p tensors, so this guy behaves transforms appropriately according to permutations, and this one does. You take that tensor product, then you get a larger tensor, but it still transforms as a p tensor. It transforms in this covariant manner. You can take the element-wise product of two tensors, and you get a tensor which transforms appropriately. You can take a tensor and you can project it along some of its dimensions, and you get a smaller tensor which still transforms appropriately. And the third thing is that you can contract over some combination of pairs or triples or quadruples of indices. So you just sum over certain sets of indices. Then you again get a smaller tensor which behaves appropriately according to permutations. Okay. So again, we are in a situation where there's this general theory and gives a particular prescription for what the neurons have to do. Okay, so this is just a demonstration of these properties. Okay, so this is what our neural network does. Actually, maybe the next figure is better. So this is the case for second-order activations, i.e. when the messages sent from each of the vertices is actually a matrix. So what the neuron corresponding to the central atom in this case must do is that it must collect all these activations from the neighbors, all these matrices, and then it stacks them up. So now we go from the second-order tensors to a third-order tensor. But stacking is also an operation that, if the stacking index corresponds to where the matrix came from, it results in a third-order tensor, which gets transformed appropriately. So that's good. Now, there's another step which is not depicted in this diagram, but we actually use in neural network, which is the tensor product operation. So we take the tensor product of this third-order tensor with the local adjacency matrix, which is a second-order tensor. So now we have this fifth-order tensor, and each coordinate behaves appropriately according to permutations. So that's very good. But then the output of this neuron must again be a second-order tensor. So from this fifth-order tensor, we somehow need to get back to second-order tensors again, right? So what do? We just apply these contractions. So we take combinations of indices, and we sum over all possible combinations of indices, which reduces our fifth-order tensor to a second-order tensor. So there are actually a number of ways of doing this. At last count, when I checked this for a fifth-order tensor, there were 32 different ways of doing this. So all of a sudden, we went from these matrices and the third-order tensor that they make up. All of a sudden, we end up again with matrices, but there's 32 of them. So something has become much richer, right? So we've captured kind of more features. But it's also good because that's what neurons are supposed to do in a neural network. They're supposed to have the freedom to capture different features and then mix them with weights that the network learns. So that's where the learnable part of this neural network comes in. It's the mixing weights of these different matrices. Okay? So you take these 32 matrices, you mix them with learnable weights, apply the nonlinearity, and that's going to be the output or the activation of your neuron. Okay? And so this, again, it looks slightly different to classical neural networks, but fundamentally is the same sort of thing, right? It's a simple tensor operation, so you can implement it in TensorFlow or something, or better yet, use our library that's about to come out, which does it fast, and apply this operation, and you train it just by backpropagation, right? This is a linear, again, just a linear operation on these Q tensors, so it's easy to backpropagate the errors to get updates on the weights. Okay, so this is some figures that kind of explain the extra richness that gives you. So in particular, the advantage of these covariant neural networks over the invariant message passing neural networks, but I don't really have the time to go into that so much at this point. So suffice to say that, again, so we tried this out on this benchmark condensed metadata set of just around 130,000 organic molecules, trying to predict various properties of them, and compare the accuracy of the prediction to the accuracy of the density functional theory, which generated the predictions in the first place, and compared to other methods. Actually, I don't have a very good plot showing comparison to other methods. So suffice to say that this is one of the top-ranking methods. The comparison is a little bit unfair because this data set also has positional information on the atoms and all sort of side information from chemistry. So it's difficult to abstract away from it. It's not purely a graph learning data set. But you can see that already ignoring all that and just going entirely by the structure of the molecules, we get an error which is lower than the error of the physical model that we got the baseline truth from in the first place. Okay. So the last part of the talk that I wanted to talk about is applying similar sort of ideas for this force field learning problem. It's something that I put up a preprint on an archive back in March, but actually the the real publication is still is still it's still in the writing phase. Anyway, so in some sense, it's like a combination of the ideas from previous parts of the talk, but and kind of elevated to the slightly more interesting domain of a non-trivial continuous group, namely the rotation group. So here again, we use the compositional aspect of this problem. So we look to take the atomic neighborhood and break it down into sub-neighborhoods. That's going to be define the network for us. But the crucial thing is that here we need to be covariant with respect to the rotation group. So what we want is that when we rotate the system, then however we represent this subsystem, we represented by this psi vector, which is written here as a ket, which is not a coincidence. It's meant to be suggestive. So no matter how we represent this subsystem of a single atom or a small number of atoms, the way we represent it, so this vector needs to transform according to some representation of the rotation group. And similarly for all the other subsystems. And then we combine these subsystems into larger subsystems. So this is like what a single neuron does. It combines these guys into a larger subsystem. So it takes these SO3 covariant vectors, and whatever it does, it needs to ensure that what comes out, so its own output, must also be an SO3 covariant vector. Okay. And so this guarantees that the whole thing is going to be SO3 invariant, and at the end of the day, you are going to get a force which has the property that, if you rotate the entire thing, all the little neighborhoods rotate, and the positions of the neighborhood rotate, and finally what you get out, the prediction for the force, will also rotate by the same angle. Okay. So it's too bad that I don't really have time to go into this. Let me just summarize that this, again, involves these ideas of convolution on the rotation group. So that's something that we're going to have to use. But there's one crucial extra ingredient, and that is the nonlinearity. So in the previous examples, the nonlinearity was essentially always done in real space. So whereas the convolution was done in Fourier space, the nonlinearity has to be a pointwise operation in the original real space. So we needed to go do this forward and backward Fourier transformation. Now doing the inverse Fourier transform on SO3 would be painful. And doing the it would require quadrature. It's hard to discretize the rotation group. So it would make the whole thing much more, much computationally demanding. And also it would introduce error at every single layer. So instead, we do the nonlinearity in Fourier space. So that's a new element. And it requires a specific tool called the Clebsch-Gordon transform, which relates to the decomposition of the tensor product of irreducible representations of the group to a direct sum of irreducible representations. Okay. So essentially what we're saying is that we can't really do a ReLU on the rotation group, but we can do other nonlinearities. For example, we can do a quadratic nonlinearity. So that's very simple. And it's not as powerful as just like this hinge-like thing for the ReLU, but using the Clebsch-Gordon transform is actually something that we can do in Fourier space. So we end up with quite a tractable thing. But it does require adding some new stuff onto these celebrated software packages, right? So if these days in machine learning, if you want to do work that other people pick up, then you need to provide the software implementation, and the software implementation needs to be in one of these guys, right? None of these guys have the Clebsch-Gordon decomposition implemented in them. So what we are doing now is we are creating our own implementation. We're trying to make sure that it's properly done, and in this context, it means that it runs on the CPU, it runs on the GPU. Maybe eventually it can be even generalized to like a multi-node clusters, and then you can just plug it into your favorite neural network architecture, and it will make the kind of mathematical complex, like hide the mathematical complexity under the hood. Okay. So again, this is very preliminary results. We tried it out in another standard molecular data set. Here, these are trajectories, so molecular dynamics trajectories of these select simple molecules, and what you're trying to predict is the total energy of given conformations. And just straight out of the box, after like 2 weeks of playing around it, we got results which on 4 out of the 8 molecules actually beat all the other competitors. And that's not because it's not because there's something magical about this network. It's not because we got the architecture exactly right. It's simply because we respect the symmetries. So symmetry is pretty important when you deal with these physical problems. Okay, so there was quite a lot in this talk. I need to acknowledge my co-authors. So first of all, Shupendu, who I already mentioned, was the inspiration for the whole thing to some extent. Sun went about, he's only a second year student, but he went about and wrote his deep learning library in C++ from scratch just for the sake of implementing the compositional networks. You can download it and then try it out for yourself. So it's like a implementation tour de force. Horace has been active in several of these projects and is mostly interested in, again, the graph case. And Brandon is my postdoc, who is a physicist by training, is very interested in the physics applications and has been pushing this n-body networks direction in particular. So the two key components, the two take-home kind of messages, I guess, from the talk, is that it's worth thinking about what it is that makes convolutional neural networks tick and how it really relates to the underlying, the structure of the underlying domain. In particular, there are two key properties. One of them is this compositional compositional nature of convolutional neural networks. So that needs to be reflected in your neural network. And the other one is respecting covariance with respect to the appropriate transformation group. All right. Thank you.
Time for questions?
Yes.
So, I'm curious as to with building in or just operating on these very specific groups, you have to do a little bit of extra work to actually operate on those in the equation. So, in that case, how is this compared to, like, let's say, like just manually, like augmenting the training data, which is a pretty popular approach for like rotational data?
Right. Right. So that and different parts to. So, I was reminded to repeat the question. So the question was that how does this compare to the more standard approach of implementing symmetries in neural networks and learning algorithms in general, consisting of just feeding not just the original data, but the transformed versions of the data separately to the neural network and training them all on them collectively. Okay. So part of the answer is that doing that for something like the rotation group would be expensive because you would need to consider so many separate rotations. Okay. Another part of the answer is that doing that for something like these physics problems might be a little bit inelegant. But the third part and the most important part is that in these sort of problems, it's not like, it's not like in image recognition where you want to be more or less invariant with respect to rotations of the image. But if you're not entirely invariant, well, that's not the end of the day, right? Because there are lots of other hints in the image, whatever, you're still likely to get the class label right at the end of the day. Here, in these two types of problems, invariance is really not an option, and it needs to be satisfied not just in a more or less way, but it needs to be satisfied exactly, right? So if you have a graph learning algorithm, but the graph learning algorithm gives a different prediction based on whether you call this vertex number 1 and that vertex number 2 or the other way around, then it's not a graph learning algorithm anymore, right? You're not actually learning from the topology of the graph. Similarly, for these physics problems, if you're trying to learn a force field, and the force field doesn't respect rotation invariance, then any kind of molecular dynamics trajectories that you get from that are going to be completely messed up, right? So you really want to respect these invariances explicitly in this case.
I'm wondering if there's any relation with the scattering transform, doing things in wavelet space. And the second question, you were indicating propagation of messages, and I was thinking the idea is very related to what you do in probabilistic graphical models, not in neural networks. So have you thought on what happens to algorithms like junction tree algorithm, where effectively you sort of link nodes together, in a certain way to satisfy certain properties to allow you to do tree propagation. Are this rotation invariant relations sort of
Right.
Satisfied at the end of the day with the junction tree algorithm?
Right. Okay, both of them are really interesting questions. So the first question was, is there any relationship to scattering transforms? And the second question is, this message passing scheme looks very similar to the message passing in graphical models and all the machinery involved, such as the junction tree algorithm. What is the analogous notion of covariance in that context? Okay, so the first part, as far as I know, the scattering transforms that have been proposed definitely reflect this compositional multiscale idea, but they are not covariant with respect to rotations. But this is something that I've been actually been having conversations with Stefan Mala and Matt Hearn about, because it's just so natural in that context. So like rotating wavelets is a little bit more tricky, but it completely fits this kind of harmonic analysis perspective, which really underlines the scattering transform.